you with Colin Snodgrass on the asteroid theme.
Okay, thank you very much.
You get 15 seconds extra.
Okay, so we've talked a little bit already about water and how it's very important, and this is why we want to go and find it on the moon. But I want to talk a little bit about water in asteroids. And particularly, I'm going to look at sort of the main asteroid belt to start with. So what I have here is a diagram that's sort of depicting what the sort of current favoured model in solar system formations called the Grand Tack. And it shows the early solar system at various times. The large black dots are the giant planets forming, and you can see that at the start of this process you have a nice disk of planetesimals forming with dry rocky things inside of Jupiter in the inner solar system and wet things outside. And then Jupiter and Saturn move in, and they come all the way in, with Jupiter coming in to, I think it's about 1.5 AU even, but then gets caught in the resonance with Saturn, and then they move back outwards. But the process of the giant planets moving around like this scatters the small bodies all over the place, and what you end up with at the bottom is you end up with the giant planets where you expect them, and some terrestrial planets of the right size, and you also end up with an asteroid belt, but the asteroid belt contains a mix of some water-rich bodies as well as what we traditionally thought of as asteroids as dry, rocky things. So, water in the asteroid. Do we know there's water there? We do. This is Ceres, which is not really representative of the asteroid belt, being much larger than everything else. It's a dwarf planet. It's big enough that it's been shaped by gravity and is differentiated, so there are models of its interior that suggest it has to have this water ice rich layer and then in a rocky layer at greater depth. We also have directly observed that there is water coming out of Ceres. So these observations with the Herschel Space Telescope, they were able to detect a signal of outgassing of water leaking out of Ceres and into space. So we know that there is some water at least there, but this is a relatively large body. Is it representative? If we go to the next sort of size down, or the sort of 100-kilometer-ish size of bodies, asteroid Themis, there were a couple of results in 2010 where reflectance spectroscopy looking at the surface around 3 micron in the infrared saw this feature, this absorption feature, which is attributed to water ice on the surface. Now, it's a bit of a puzzle while you see it there. You don't see other water ice features at shorter wavelengths, so you have to do interesting things with particle sizes to fit the model. And there have been a couple of papers suggesting, well, you can get a similar feature with certain minerals, but then you have to explain why you have this thing covered in a fairly rare mineral. And further observations have revealed similar features like this on many of these large-ish, the 100-kilometer scale asteroids. So if we believe that this is water, or at least is water-related mineralogy, then it seems that the largest asteroids possibly have water. But what about typical asteroids? Typical asteroids are small, kilometer-sized thing. There are far more small ones than there are big ones like this. Well, there's evidence that there are wet asteroids in the smaller size range, because we see these things that look like comets. So they're called either active asteroids or main belt comets. There's images of a selection of them here, and this is a plot that shows the orbits, the orbital elements, semi-major axis and eccentricity. In this, you have the orange points showing a representative of the asteroids and the main asteroid belt. The blue points are comets, so Jupiter family comets, which we know are full of ice. But the red dots here are these things that have asteroid-like orbits but show comet-like morphology. They show tails. And something has to be releasing the material from these bodies. You can explain some of them with collisions and debris between them, but for some of them they repeat, and the repeating nature of this activity each time they come past perihelion, like a normal comet, indicates that their activity, this dust release, is driven by water. However, what we'd really like to do is get direct evidence that there's water in these things. They're too small and faint, these small asteroids, to look at reflectance spectroscopy in 3 microns. They are The activity level from them is too faint for Herschel. We did try with Herschel, but we only got upper limits. So what we want to do is look at the other gas species or fluorescence of various daughter species, the way that we'd look at a normal comet. This is an example comet spectrum, a typical comet. The top shows the sort of larger features, and then it zooms in at the bottom on the relative intensities. You see there are very strong features there from hydroxyl at about 308 nanometers, and from cyanogen at 389. So these are the sort of strongest features you see in a normal comet spectrum in the sort of UV optical range, so the easiest range to observe from the ground. The 308 nanometers OH band is very strong, but from the ground it's difficult to observe because it's absorbed by ozone there. So mostly we look at comets for CN at 389 nanometers. We've tried this with various of these main belt comets and not detected any of the gas via cyanogen. But then there's been some theoretical studies that actually look at the survival of ices within these small asteroids and how they would be heated over their lifetime in the solar system. And what they found is that actually you only expect water. You don't expect more volatile ices. Things like cyanogen we expect comes from something like HCN as a parent ice, which is far more volatile and will disappear a lot earlier on in the solar system. So actually, maybe we don't expect a CN and we have to go and look directly for water or its direct products like OH. Directly detecting water is very difficult from the ground, of course, because the atmosphere is full of it. You can look at very high resolution in the infrared, but that only works for a bright comet. You can look at these daughter species, OH or oxygen, and you can look from outside the atmosphere is the best approach. So space telescopes are probably the best way to go, and possibly this very strong line at 308 nanometers is the best one to reach. If I now think a little bit about comets and how bright they are and what sort of signal to expect, for a very bright comet, something like Hale-Bopp, it had production rates of order 10 to the 30 molecules of water per second. If you have a comet that's producing that much water, it's very bright. You can apply all sorts of techniques, high resolution spectroscopy. You can even measure things like deuterium to hydrogen ratio in the water from the ground. No problem in actually detecting water there. For a typical comet, something like 67P, Rosetta target, when it's at perihelion at a peak rate of about 10 to 28 molecules per second. We can't measure things like deuterium hydrogen from the ground, so we sent a spacecraft there to do it in an expensive way. But we can detect things like OH. We can show that a comet like CG does have water and measure a water production rate from ground-based telescopes. But for main belt comets, you're looking at orders of magnitude below that again in terms of production rate. To produce the amount of dust that you see coming off of these things, you need only 10 to the 23, 10 to 24 molecules in the water, which is way below detection limits on current ground-based telescopes. For example, El Pizarro's 133P, this is the first main belt comet discovered. We did some rough back of the envelope numbers, and the sort of rate you're getting if you have a small telescope out of atmosphere are in this sort of tens of photons an hour sort of a rate, which is difficult to detect, but not impossible. So one of the things that I'm studying and one of the things that we're interested in is, can we go and search for where is the water in the solar system using a relatively small UV telescope? And the whole point of this is to look at a dedicated mission with one particular goal. So the instrumentation, the telescope, it's all designed to look at this one band, this OH emission at 308 nanometers, and say, is it there or not? And look at lots of asteroids. And with this, you could do with a sort of small class mission, this sort of platform. This is an image of this Cheops, which is a ESA S-class mission for doing extrasolar planets, but it has a 30 centimeter telescope in it. Something of that scale is relatively cheap mission for agency type basis, and could be the sort of thing that even a motivated single country could do, or a couple of countries. It's the sort of small scale mission, and I think there's a very interesting science goal there in saying where is the water in the solar system for doing it. It has various other goals as well as main belt comets, of course. There's all sorts of other wet things around the solar system, and where is the water is a very interesting question for planetary science. The other approach to doing this, of course, is to do it in a larger mission. You could do the same science with a large UV observatory, so the next generation post-Hubble. If you have the right instrumentation, then you can also go and do deep searches. You know, a bigger mirror definitely helps you, but of course then you're competing with all of the astrophysicists who want to point at other things. The alternative approach is you could do it as part of a larger mission, which is a wider planetary science mission more generally. So, for example, there's a mission that we're working on at the moment and considering for ECM5 called Castaway, which will be which is proposed to do a tour of the asteroid belt and study a lot of asteroids using a telescope, and this will also have a capability to do this sort of search for water. Or finally, you can go and just directly detect in situ with mass spectrometers, but that only works for one target at a time, and that's a completely different sort of mission. That's also possibly going for M5. So just before I end, the one thing I wanted to look at was near-Earth asteroids and how they fit into this picture, because I've talked about some main belt comets and where we think there's water in the asteroid belt. Is there water closer to Earth that we could potentially look at as a resource? Well, the near-Earth asteroids, they all come from the asteroid belt. So if there is water in small asteroids in the asteroid belt, there's a good chance that there's also some water in some asteroids in the near-Earth population. Near-Earth ones are closer and therefore for the same sort of size, are relatively bright. They're warmer, so there's going to be a higher rate of gas escape from them. But we don't see the same dust tails around anything like the main belt comets so far in surveys. So clearly there's some search there to go and find out where is the water, which ones have water. But a similar sort of survey could be quite interesting in that case, and is interesting for prospecting for potential mining as much as it is for planetary science. And one of the other things we've been talking about is even to go smaller than this S-class type thing. And at least as a proof of concept, as a pilot for this, it would be quite interesting to try this even with CubeSat-sized things. I've been having some discussions with people about deployable telescopes in CubeSats and so on. This thing's being developed in various places, including UK ATC. And we're looking to get a summer student to have run some simulations on these, run the numbers, how much water should there be in various places. So just to conclude, there is definitely water in the asteroid belt today. We know it's in the biggest ones, and it looks very probable that it's in these small ones that show some activity. The question is how much water is there? What fraction of the population is really active? What is their water coming out? It's a very important scientific goal for looking at the formation of our solar system and trying to understand better these theories of how you form things. But of course, as we've been hearing, water is also a nice valuable resource, so there's a potential overlap here in the commercial interest in doing a similar thing. So doing a small, cheap observatory type thing in the UV, I think has a very high science return and is something that I propose as a useful science mission, but it's possibly something that will also be of commercial interest. With that, I'll stop. Thank you.
Thank you. We have time for a couple of questions. If the other Colin could come up as well, just to be ready. Questions? They're all lunar people here, obviously.
Yeah, everyone's lunar.
Yeah. Yes, Jim.
If you had to make a guess, order of magnitude?
For what? For
Mass of water in the asteroid belt.
it's.
Ceres has got to be almost
I mean,
more than the Earth.
Yeah, I mean, Ceres itself has a lot.
25%.
Yeah, there's a nice image which I didn't include in here, which you see, which is if you took all of the water of the Earth and put it into a small ball, it's a ball about the same size as Ceres. But actually, the amount in Ceres itself is also quite large. And Ceres dominates by mass a lot of the asteroid belt anyway. So there is quite a bit there, but how much is accessible in the smaller stuff is an excellent question.
Because the reason I only mentioned that is, I mean, there was one comment earlier about, let's say, the sanctity of the lunar environment, in that it's far more of a cultural icon to civilization than asteroids in the asteroid belt. So we may well use lunar volatiles as a springboard to expansion into space infrastructure. But I don't know whether it would be the near-Earth asteroids, but perhaps the asteroid belt, even as sparse as it may be in real terms, geometric terms, could be the real follow-on 50 to 100 years after we've used the moon.
You know, there are many asteroids, and I don't think anyone would miss one or two if you were to strip mine in the water. So.
Indeed. Okay, I'm afraid we have to stop there. Let's thank Colin again.